This video is going to cover concepts 4 and 5, gravitational potential energy, and conservative and non-conservative forces. So concept 4 is on gravitational potential energy. The concept of gravitational potential energy is just that when you lift something up or when something is raised up, that it gains energy. And it doesn't matter where you're lifting it up from and where you're measuring from. It's basically the change in the height or the change in the y direction that is giving it the energy. And so we have this formula. PE is what our textbook uses for potential energy. U is what our AP uses for potential energy. I might call that U sub G for gravitational potential energy. And then mgy is just mass times gravity times the height. The AP sheet actually calls it mg delta y, and I wrote down here mgh, but so on the AP sheet it is mg delta y. Let's take a look at some equations, and some problems to look at how to use this. First of all, just to point out again that y is the height above an arbitrary position. In other words, it doesn't have to be like the height above sea level or anything else. It might be the height above your table. It might be the height above the floor. It might be the height above whatever you are wanting to choose. So your zero height could be anywhere. So let's take a look at number 6. If a 25 kilogram crate is lifted to an elevation of 2 meters, what would be its stored gravitational potential energy? Well, once again, I probably should have a U sub G here on this one. Let's put a G there. So that's what we're calculating is our gravitational potential energy. And we know the mass is 25 kilograms. And we know that gravity is 9.8 meters per second squared. And the change in elevation was 2 meters. And so I multiply this out. And when I multiply it out, I get 490. And let's take a look at the units. The units are kilogram meters per second squared. That's like a Newton, times meters. Well, Newton meters is a joule. So that is 490 joules. Let's take a look at example number 7. This one is phrased a little bit differently. This time we're asking about work, but remember work is just a change in energy. So we're really talking about the same thing here. Our equation for work is F sub x times delta x. In this case, of course, we're actually talking about the y direction. So if we want to rewrite that with the y in it instead, we could. And we could also call it W net just to make it a little bit more accurate or a little more specific. So we have F net is F sub y times the change in y. F sub y, that's just m times g. So it's really just, I'm going to go ahead and finish this out, but it's really just the same thing that we've been talking about. We have F net equals m times g times delta y. Now look at what I just wrote. I got mg from F sub y because F equals ma. But now look at what I have. It's the same equation that we've been talking about, mgy. So our work net, we can go ahead and plug in some numbers here. Our work net is the mass, which is 25 kilograms again. Gravity, 9.8 meters per second squared. And our delta y is 2 meters. And so once again, we have actually the same answer as before, 490 joules. So basically, if we look at these two examples, they both come up with an answer of 490 joules. Let's look at what the question was even asking. On the first question, it's asking for the stored gravitational potential energy. And the second question has the same information, but it's asking how much work would be done to move it. Well, remember that the net work is the change in potential energy. And I think there's a spot there for the bottom. Here we go. So the net work is the change in potential energy. In other words, by lifting it, you did 490 joules of work, and that added it to the system. So your change in energy added energy to the system. It added to its gravitational potential energy. Typically, it would have just rearranged it somehow, but in this case, you've done work, and so that means you added energy in. So the net work is the same as change in potential energy. And I'm going to put a G there, but really it could be change in any energy. In this case, we're talking about potential energy. Let's turn the page. Okay, conservative and non-conservative forces. what we are talking about with conservative and non-conservative forces is a force is conservative if the work it does moving an object between 2 points is the same no matter what path is taken. They have some examples here. If we look at these examples, these two swimmers, divers, whatever, took 2 different paths. This person dove essentially going straight down. This person took a slide where their action had a much different path, but yet their change in energy was exactly the same. That is conservative. That is conservative because they didn't lose anything, and the gravitational force, it doesn't matter which way you go. You can zigzag your way down and you'll have the same change in potential energy as you would if you just jumped straight off. So that is a conservative force. However, frictional force, if we think about this, the definition at the top again was a force is conservative if the work it does moving an object between 2 points is the same no matter what path is taken. Does this have the same work whether we go this long way from A to B to C to D or whether we go the short way? Well, no. First of all, there was no change in elevation, which typically conservative forces are gravitational forces change in elevation. But also we know by friction that some energy will be lost. So if we take a look at this, frictional force is a non-conservative force because it definitely matters which path you took, because you will have a different result from each path in this instance, whereas in the swimming pool instance, there's not going to be a difference depending on which path you took. Okay, so we have a work energy theorem, and the work energy theorem is given by the non-conservative work plus the conservative work adds up to be the total change in kinetic energy. And that's what it says down here. NC is the work done by non-conservative forces, and WC is the work done by conservative forces. But again, basically we're saying that if there are some non-conservative forces involved, you have to add those into the equation. So the work by a non-conservative force is calculated using the following equation. The non-conservative work is this. Can you see that this is the change in kinetic energy right here? So this is the change in kinetic energy, and this is the change in potential energy. And so the change in kinetic energy plus the change in potential energy is going to add up to the non-conservative work. And the non-conservative work, again, would be like energy that was lost through friction or other means. Okay, this next section says, rewrite the preceding equation to show how the initial energy of an object is related to the final energy if there are only conservative forces acting on it. So in other words, if all of our non-conservative forces add up to 0, then what happens to this equation? Well, if they're all conservative and non-conservative is 0, then we can plug a 0 in over on the left-hand side. So we're going to start with the original equation we had, and we're going to set it equal to 0 now, because we're saying, let's say that there are no non-conservative forces. Everything's conservative. Okay, so we set it equal to 0. Now let's rearrange it so that we have all of our initial information on one side, and we have all of our final information on the other side. So the initial I'm going to add to the left, and this initial I'm going to add to the left. So I have Ki plus Ui because those are my initials. They used to be negative, but I moved them over, and when I moved them over, they became positive. What I'm left with on the right-hand side is my positive K sub F plus my positive U sub F. And those are just what was there originally, and so that is remaining there. Notice we have that the initial kinetic plus the initial potential is equal to the final kinetic plus the final potential. And that is conservation of energy. That is saying we are conserving the energy, that the same energy we had to start with is the same energy we had to end with. And that's what we've been doing with our LOL charts. So in other words, energy is conserved if there's no non-conservative energy. In other words, we're not losing anything from friction, we're not losing anything from sound, what have you. We have everything as being conservative. That means we have conservation of energy. Initial energy is the same as the final energy. This equation and this setup comes to be pretty important. There are a lot of problems that we are going to do in the next couple of days that are going to require us to understand this concept of conservation of energy. And so really make sure you understand how this equation is working, how this is set up, so that when we start to do some problems like this in class, you have a good basis for what we're doing.